time.
Vicent is about to give us a rundown of exactly, perfectly, to the line by line. I might be overstating what Vicent's exactly about to talk about, so I don't want to sort of oversell him. But we are going to learn about the internals of Ruby. Please put your hands together, Vicent!
Thank you. Thanks, everyone. I'm going to see the slides. Oh, nice. Fancy. I like it. So, hi, everyone. Once upon a time, in a country far, far away, the magical country of snow, there used to be a young man. Actually, it was just me. I was living in Finland a few years ago, and I was in an indie video game studio. And I woke up one morning and I was like, man, it's so cold in here right now. Like, maybe if I had a real job, I could afford paying for heating in my house. So I went to San Francisco to work for a startup called GitHub. But that was 3 years ago, back when we were like 10 people. Now we are much, much bigger. We are like 217 people now. And things have changed a lot since then. But my job is still the same. I'm still on the GitHub systems team. And we are the team that doesn't really write Ruby, which is a shame. We are the team that kind of deals with MRI, which is also a shame, actually. Today, I come here to talk to you about horror stories from the GitHub systems team. These are things we found over the years when trying to do a huge, massive Ruby deployment in production. Because you probably know that GitHub has one of the largest Ruby deployments in the world. And these are some of the tales that we have found over the years of horrorful things that have happened to us. There are many of these tales. I could have chosen many of them. I chose 3 of them to tell today because I thought they were the more interesting. I thought they were the most relevant. Like if you ever run a huge Ruby deployment in production, it's very likely that you've ever seen one of these things. And I have decided to tell these stories like if they were fairy tales, because I have a lot of spare time. Like I just sit at home, I don't know what to do. So shit like this comes out. The first tale is called Mark and Sweep, the dumb tale of a dumb garbage collector. So the legend says that inside of MRI, inside of Ruby, there lives a magical creature that takes care of eating out the memory that the program is not using anymore. There is very little known about this creature because all the stories, all the tales that have ever been written about it, they are written in a very ancient language full of arcane glyphs that I don't understand. What was the name? Oh, Japanese. Yeah, the dogs are in Japanese, so I don't really know what's going on here. But what we know is that the Ruby garbage collector is like a two-headed monster. It's like 2 monsters in one, 2 heads in a single creature. The left head is called Mark, and it's a dumb one. And the right head is called Sweep, and it's still pretty dumb, but not as dumb as the other one. In general terms, the Ruby garbage collector is conservative, which means that it doesn't really know what it's doing. Non-deterministic, which means that it does it very poorly. Stop the world, which means that it hates you and it hates your Rails app. It really does. And Mark and Sweep, which is what we're going to try to explain here more or less today. So basically, it's a shit show, to sum it up. Okay, so you run your Ruby app on MRI, right? And you run the memory, and you're like, okay, Mark and Sweep needs to go in. And what happens is that first we bring in Mark, the left head of Mark and Sweep, to do his job. Mark's job is pretty complicated. It has to walk the object graph, and it has to look for things that look like Ruby objects. What does it mean? Well, when you're in actually Ruby land, like when you're in your Ruby code, it's very easy for Mark to find the objects that you are actually using. Like it starts in the global namespace, you got classes, you got constants, and it starts marking all that because you're obviously using all that. But it gets much more tricky because Ruby handles raw pointers to C extensions. When you're running a C extension inside of MRI, the code of that extension is using Ruby's C API, and all the pointers to Ruby objects it has, those pointers are in the native C stack. And we got a very dumb garbage collector that has to go through the Ruby C stack and try to find those pointers, and this is a very non-trivial thing to do. The garbage collector must find those roots in the stack, in the heap, and in the registers of the native virtual machine, which is so incredibly complicated. It needs to walk down a native stack of your platform, which is x64, for instance, and it needs to find every single piece of memory that looks like a variable. It needs to tell if it's actually a Ruby object or if it's not. So in practice, it looks something like this. Like Mark goes around, and he's like, this kind of looks like a pointer, doesn't it? And Sweep is like, I guess. Can I try freeing this? Is this going to work? You can try, see what happens. This is actually a dramatization, because in the real world, the Ruby garbage collector doesn't really talk in a very funny comic voice. Or maybe it does, because the docs are in Japanese, so I don't really know. So, anyways, once the marking phase has gone over, it's time for the sweep phase, which is the easy one. Because sweep has a list of all the objects that have been allocated, and now we only need to free the ones that have not been marked, because it means those are not being used right now, right? But here's the huge, huge problem here. That there is memory allocated by the Ruby garbage collector that the Ruby garbage collector cannot detect. Let's look at the example, showing some C code. Sorry about this. We have a Ruby extension, which is actually C code, and we got a value, which is a Ruby object, which is actually a string in Ruby land. If we want to work with that string, we need to call rstring_ptr, which is going to give us the pointer to the actual buffer inside of the string. Because in C land, the Ruby object is an opaque pointer, but inside of it, there is the actual bytes that make the text in our string, right? So when we are in a C extension and we access that internal buffer, usually what the compiler does is it places the pointer to the buffer on the stack. And here's when things get very dangerous. When we got that pointer to the internal buffer, it's in our stack, we can do things with it. Like we can call other C functions with it. And the Ruby garbage collector makes a huge assumption, which is that if we call a function using that pointer, that internal pointer, the value, the actual Ruby object, will stay on the stack. This is not necessarily true. Like if you call a function, the compiler can optimize out the actual Ruby object, remove it from the stack, and only leave the pointer to the internal buffer inside of it. So what happens when a garbage collection run happens when you are inside of that function? Well, Mark, which is pretty dumb, goes through the whole stack and tries to look for Ruby objects, but it doesn't find that string. It only finds the pointer to the internal data of the string, which it cannot mark. So Mark is like, oh yeah, go through the stack, yes, yes. Climbs up the stack, only sees the char, which means that there is a Ruby object, we have this pointer to the internals of the object, but the object itself is gone from the stack. So it doesn't get marked. Mark doesn't mark the actual Ruby object, and when the sweep phase happens, well, sweep goes through every single thing, and it's like, this is not marked, we can free this, and it actually frees the Ruby string, which means that the internal buffer gets freed too. This makes sense, like the Ruby object is not in the stack, but the internal buffer is. And now both of them are gone, they both got freed. So what happens when you try to access this from CLAN? Well, I don't know what a segfault sounds like, but I guess it's like an explosion. Like, what was that? I don't know. You broke something. I didn't. You may think this is not really that relevant, but it's actually extremely relevant. This used to happen all the time with Bundler, the famous Z-lib bug, and it still happens a lot. If you're running a huge deployment of Ruby in production that has C extensions, it's very likely that eventually you will trigger this bug, and your server will just crash. It will go down. So how do we go about this? Is there a way to work around this issue? Because it actually happens. There are several ways I want to show today. The first one, which works very well for me, is drinking myself to sleep every night. There is this legend that... Thank you. There is this legend that says that if production goes down and you're passed out, they can't really blame you, right? So it works so well for me. Plan B, more professional. We can stress the garbage collector on critical path. which is a very fancy way of saying you just make it run until it catches fire, and then you watch the fire. Oh, pretty. So how do we do this? In CLAN, we just change our memory allocator so it uses a perturbation mode, which means that every time it frees memory, it will overwrite it with trash. This is very useful because it means that if we try to access memory that has been freed, we will always crash, which is super handy. There is also, in Rubyland, we can enable the GC stress mode, which means that every time there is a garbage collection check to see if we need to run garbage collection, the check will return true, which means that garbage collection will run all the time. This way, if there is this bug anywhere in your code base, it will be triggered and you will be able to spoil it on the wild without having to keep trying. If you want to be even more accurate, you can use Valgrind or address sanitizer instead of tampering, which is a C program that hooks into the memory allocator and tells you exactly if you are trying to reuse memory that has been freed already. This is very accurate and very specific. It tells you exactly where is the bug, but it's got the problem that it's a very expensive hook. It hooks into the garbage collector, which is kind of slow too, which is into MRI, which is slow too. So in practice, if you try to run this with a Rails test suite, well, you can compare this graph compares the time it takes to run your Rails test suite with the heat death of the universe. So yeah, my advice is to bring a sweater because it can get cold towards the end. And you can also use static analysis, but I don't want to talk about this because usually there is a Ruby conference, and if I start talking about static analysis, people just jump out the window. So I don't want to do that. Anyway, I'm just going to move over to my next tale. It's called Our Time is Running Out, and it's a tale about timeouts. So when I joined GitHub, I was a game developer. I didn't really do Ruby stuff. I was like, how do I Ruby, right? I don't Ruby at all. So I started writing some backend software, and I wanted to add some timeouts to it. Because if you are trying to build a distributed system, you want to make sure that all the network calls, all the expensive operations have timeouts, so they can really block and take down your whole system. So I did that. I wrote a small piece of software, and I showed to one of my coworkers, Aman. I was like, yo, Aman, how do you feel about my timeouts? And he was like, there are no timeouts in Ruby. I'm like, are you sure about that? Like, have you looked properly? Because they're going to be like, after there's the module and the standard library and shit. And he's like, no, in fact, there's this legend that says that there is a white rabbit inside of MRI that brings the timeouts. But the white rabbit, like in the tail, it's always late. I was like, that doesn't sound realistic. Can we try this out? So I went on production. I actually tried this out. Like, I required a timeout module. I added a timeout block with a long-running operation that was supposed to run for a minute. And I added a 5-second timeout to see how this worked. So I just set that to run, and I waited 5 seconds. I waited 10 seconds, 20 seconds, 30 seconds, a minute. And then finally, hey, there's a timeout. Whoa, you're like a minute late. This is not very useful anymore. Like, this is not good at all. And the poor timeout rabbit, he was choking. He could barely breathe. He was like, I'm sorry, I just got here, but I just couldn't come any faster. And I was like, timeout rabbit, what happened to you? Why were you like a whole minute late? What's going on here? And the timeout rabbit explained to me how timeouts work in Ruby. He showed me this. This is how we implement timeouts in the MRI standard library. It's so straightforward, so beautiful. Basically, when we want to timeout something, we start a new thread, and we put that thread to sleep. So if we want to timeout for 5 seconds, we sleep the thread for 5 seconds, and when it wakes up, it will raise an exception on the main thread, and then that will time out our process. And when I saw this the first time, I was impressed, because this is beautiful. This is beautiful code. I told the rabbit, this is beautiful, this is gorgeous, this is elegant. And the rabbit said, yeah, also it's broken, it doesn't work. So the rabbit started explaining to me. He said, you know, the issue is that in MRI 1.8.7, the classic version of MRI, the actual threads are implemented as green threads, which means that the threads are scheduled inside of the Ruby virtual machine. The actual interpreter schedules the threads in userland. So when we're actually trying to time out something, for instance, a network call, when you perform the network call, that will go to the kernel, and the kernel will put your whole Ruby process to sleep. The kernel doesn't know that there are green threads inside of the Ruby process. So when you do the network call, the process will get to sleep, and the other thread, the one that has to wake up to time out your main thread, it will never wake up because the kernel doesn't know it exists. So once the actual call that lasts a minute finishes, the kernel wakes up the whole process, and that's when the timeout thread wakes up and you get the actual timeout, but that's 1 minute late. The long operation has already finished, and it didn't time out because the timeout thread didn't get scheduled. But I told the white rabbit, obviously this doesn't apply because everyone's using Ruby 1.9 now. Yeah, not really. No one uses it. The thing is that the same thing still happens in Ruby 1.9.3. Ruby 1.9 now has native threads, which means that the kernel knows that the threads exist. It schedules them manually. The kernel does it. But when you actually want to run a Ruby thread, you need to grab what we call the GVL, or GIL in Python land. It's a global VM lock. So here's the issue. If the thread you're trying to time out goes into kernel mode, and it hasn't released the GVL, the kernel will see the other timeout, the timeout thread, and will try to schedule it, but it will not be able to, because you can schedule the timeout thread, and it will be like, I can't grab the GVL, because the GVL is currently owned by the main thread that's being asleep right now. And without the GVL, the timeout thread cannot raise a timeout exception. So it will simply not time out, again, until the kernel wakes up the main thread and your whole operation is over, when the timeout is no longer relevant. So this basically blew my mind. Like, I was very worried about it, because I wasn't expecting this to be such a hard problem, and I really didn't know how to work around this. And I went home. I was like, I'm giving up on this Ruby stuff. I don't want to Ruby anymore. But that night, I had a dream. I dreamed I was in a swamp, and these old men show up. And I said, Obi-Wan Kenobi, is that you? And the man said, I'm actually Dennis Ritchie, the creator of Unix and the C programming language. I was like, sorry about that, Dennis. But then Dennis told me, yo, VMG, use the Force. And I was confused, because I thought you were not Obi-Wan, man. What's going on here? And then Dennis told me, Unix, you moron. Unix is the Force. I suddenly woke up, and that morning when I woke up, my laptop had magically opened on the terminal a man page. The man page for alarm, a syscall that lets you set a signal handler that will wake up after a given amount of time, which is a very, very, very elegant way to solve the timeout issue in Ruby 1.8 and 1.9. It basically means that you can set a timeout that the kernel will manage, and after these 3-5 seconds, as much as you want, the kernel will run the signal handler and will force the scheduling of your Ruby process. From there, you can actually wake up whatever thread you want, and you can raise the timeout exception. So there is a very elegant solution about it. There is a gem that already works. It's called System Timer, and it works very, very well with 1.8.7. It does reliable timeouts all the time. And if you're in 1.9.3, you can use this gem, which works very well, or you can just make sure that every time you do a long operation in CLAN, in the kernel, you always release the GVL before going to the kernel. If the GVL is locked, you cannot raise a timeout exception, so it will not time out. So this is a elegant, beautiful way to tackle timeouts in MRI. And I thought that was the end of the story, but a few months later, I went to another magical country on a trip to meet a very, very old friend of mine. His name is Matthias Mann the Wise. He lives in a magical country called Berlin. But you may know him from his real name, Matthias Meyer. He's the head honcho of Travis CI. If you don't know what Travis CI is, please ask me later, because it will change the way you write software. Travis is awesome. And he works at Travis. He also has a very nice book called the React Handbook. And I don't get paid to say this. It's actually a very nice book. If you're running React on production, buy the book. It's so good. I went to Berlin to do the usual thing, talk with the old wizard and discuss programming stuff. And we had this conversation, and the wizard told me, you see, I also had a dreadful problem with timeouts. I said, oh, wow, really? Just like us. Let's talk about it a little bit. And he said, you see, I was using JRuby, so I interrupted the wizard. I said, wait a second, you got a problem with timeouts, and you're using JRuby? Well, it sounds like you have two problems now, right? And then the wizard told me, shut the fuck up, kid. You see, I was using the JRuby with the GitHub API that you guys keep breaking, which is fucking disaster, you fuckers. And we had this issue, like we had this very big background process in our server for Travis CI for queuing up builds. And we had a very specific timeout set to make sure that if GitHub was taking too long to answer, we wouldn't go down. Like it would time out after a moment and show an error. But somehow, something happened, and GitHub started taking a long time to answer, but we were not timing out. We just started piling up jobs, because we couldn't time out our request to the GitHub API, and suddenly our whole production system went down because we had so many timeouts that didn't trigger. So of course I told the wizard, well, that's obviously because your timeout thread is sleeping or is stuck on the GVL. And then the wizard grabbed his magical wizard staff, and with a very swift movement, he did boom, like this, hit me on the head, and he shouted, "You fool, JRuby has actual native threads, it has fine-grained locking, so all these issues don't really affect JRuby." He was very upset about it. He hit me to the ground, I passed out, and when I woke up a while later, the wizard explained me exactly what's going on here with JRuby. In an old version of JRuby 1.6.7, there is this dreadful bug, which is that if you got two timeouts nested inside of each other, the longest one will take preference. Like the 60 seconds timeout is not going to trigger until the 5-second timeout has triggered, which is terrible because they had a very long 5 minutes timeout inside of a 5-second timeout. So the 5 minutes timeout was getting into effect, and that was basically working up the whole worker pool and taking on production. This is a pretty serious bug. It's very hard to spot. It took them a while to figure out what was going on. But I like the bug because here I think that JRuby wins. Because, I mean, the bug in MRI, like if you have to compare it, like this is a pretty bad bug. The one in the JVM, nested timeouts, it's pretty to the right? When it comes to bad bugs, this is a pretty bad bug. But if you compare it to the one in MRI, like I think the one in MRI is like even more to the right. Like you just keep going to the right, and you leave the realm of bugs, right? Keep going, you walk to the valley of common sense, you keep walking, you climb the mountains of reason, and you keep going, you eventually reach the country of what the hell are you doing? And then you see MRI doing timeouts in green threads. Like you didn't think this through, right? But this is a good thing, because it brings us to our last point for my talk, a last tale, which is called The Princess in the Glass Tower. You see, when I began talking today, I said I chose these 3 stories. I could have chosen so many more, because we've had so many issues over the years. But this happens all the software. But when it comes to MRI, like the big issue we've always faced with MRI is that it's starting to lag behind our times. Especially the 6-tension API in MRI is a massive handicap when it comes to bringing the virtual machine into the 21st century. It's a huge handicap that shows in every single thing that changes in MRI. Like the new incremental garbage collector is severely handicapped by the way the 6-tension API is designed. It needs to use partial barriers for objects that cannot be tracked across the Ruby 6-tension layer. It's the same issue that we saw with the seg faults at the beginning. It's the same issue with the thread locks, with the GVL and the timeout model, the way that threading works in MRI. And that's the big issue. We want to do so much with Ruby, and MRI is holding us back. It feels like Ruby is trapped in a glass tower, and there is no way to go around it, because there is so much legacy code here in MRI that we can just scrap it over and start from scratch. So how do we go about this? There's a bunch of people, a bunch of very, very brave warriors that for years and years and years have been trying to work around this by rewriting Ruby from scratch. It's so much work. They've been doing this for over a decade, which is crazy, right? And they are so far and yet so close, because the issue is Ruby is it's such a very fast-moving target. Ruby core moves so fast, adding new features, and just changing the way the virtual machine works, that for every single other implementation, it gets incredibly difficult to catch up. They don't only have the work of doing a virtual machine for the 21st century for Ruby, they also need to keep up with the actual Ruby language, MRI, which moves incredibly fast. And they need so much help with this. Rubinius and JRuby, which, as far as I'm concerned, are the future of Ruby, they need so much help from all the community so they can eventually take over. And you may think that this is not something you can do. You write Ruby, you can really go and work on the JVM or write C++ for Rubinius, but it's not true. Like, I bet that most of you have an open source gem on GitHub, and simply going into that open source gem and making sure that the test pass on Rubinius, that the test pass on JRuby, and writing down the README, just be like, this gem works on Rubinius and JRuby. That means sowing the seeds for a brighter future for Ruby. It really means it. Like, Rubinius and JRuby have been on the makings for over a decade now, and they're still very far away. But we need that final push. We need a final push so we can get to the point where Ruby is not only MRI, where Ruby, the language we love, is many different implementations for different goals, and especially implementations that have been thought up from the bottom up to be working on the 21st century, which is very important to us. So yes, I know that as a fairy tale, this is a very shitty fairy tale. This is shit, basically. This is a terrible fairy tale. But I really care about this. I really mean it. I really care about Rubinius. I really care about JRuby. And I would really like that. I guess that you're here now. It's pretty warm outside. And you're here listening to me talk shit about Ruby. So I guess you actually care about Ruby. So if you actually care about Ruby, if you care about this language like we do, if you want to build companies using Ruby, if you want to bring Ruby into the 21st century, we really, really need to get working on Rubinius and JRuby. We really need to propose alternatives to MRI. We really need to have VMs for different specific goals. And we need to have a more varied, a more rich Ruby ecosystem. So please, if you really, really, really care about Ruby, please help us rescue our beloved Ruby princess from its glass prison, which is MRI. Please help us write JRuby, help us write Rubinius, and help us write a happy ending for this fairy tale. Thank you. Doc.
Fantastic.
Thank you.
Except for the bit where you criticize Ruby. I could hear everything, and luckily I wasn't the person that made Ruby, who happened to be sitting in there crying. And
sorry.
All right, questions. What have we got?
I heard you say that Rubinius and JRuby are the future of Ruby, and just sort of wonder if you could elaborate on that a little bit about the why.
Well, you probably know there is a ton of Ruby implementations going on right now. Some of them very exciting, some of them less exciting. But at the end of the day, what we see is that MRI, while being a nice VM, like I've been to many conferences talking about MRI, it has a huge bonus, which is it's a very unique C VM. In the Python style, writing in C, very tiny, it can be ported anywhere. And it's still the reference for the language. But when it comes to the 21st century, if you're trying to run huge Ruby deployments on production, it starts to lag behind. It just does. It was designed in 1993. That's a long way. And of course, this design can evolve over the years, but it has all this crust, or not crust, but all these legacy design decisions that are simply too late to change, like the Ruby 6 extension API. So as far as I'm concerned, like, more and more, we start needing new Ruby implementations. And when it comes to those Ruby implementations, Rubinius and JRuby are the two big ones because they are the ones that are backed by huge companies. It's a lot of work to do a Ruby implementation from scratch, as you can definitely imagine. And those two are the implementations that have people working full-time on them, have people with companies behind them throwing money, which is very important for these things. So as far as I'm concerned, yes, I see the future of Ruby from Rubinius and JRuby. Rubinius in the Unix way, JRuby on the Java way, and mRuby for the actual Unix. I don't know if you heard of mRuby. It's this minimal Ruby implementation that Matt is doing, which, as far as I'm concerned, would be the replacement for MRI. It would be a very unique C Ruby that can be embedded, can be used properly from C, and with a proper C extension API. But all these things, they are just not backwards compatible with the way that MRI was engineered. So I feel that there is a very bright future to Ruby, but it needs to go through more modern VMs. Like it happened with the JVM. Like we used to have only one JVM. Now there are so many different JVMs. And it's so important to have them, to have those choices when it comes to running Ruby in production, because everyone has different needs. And when MRI came out, it was the VM. It was the thing that makes more sense back then. But right now, with people who are trying to run huge Ruby deployments, we have more complex needs than ever, and MRI is starting to lag behind.
Is GitHub running any stuff in production using Rubinius?
That's a good question. I actually wanted to come here today and give a talk called Rubinius I Want to Believe, because last year a good friend of mine was throwing a Ruby conference, and he invited me, like, could you please come to our conference, talk how you use Rubinius in production on GitHub? I said, yes, I can come, but it's going to be a very short talk. It's going to be like, we don't. And that's the extent of it. But Rubinius is something I really care about. It's a piece of software that it's very dear to my heart, and I've been trying to get this going on GitHub. But the main issue we have right now is that the main GitHub app is a monolithic Rails app, and it was never designed, just like MRI, with thread safety in mind. It's not thread safe at all. So the big wins that we would get from running a Rails app in Rubinius, they are basically gone because we cannot really run in threaded mode. So as it stands right now, yes, I would love to get Rubinius running on GitHub, but it will have to start by writing small specific pieces of the backend, porting them to Rubinius, because right now porting the main Rails app, github.com, to Rubinius is just unfeasible right now. It's too much code already tuned and designed around MRI to really port it over.
Any questions, Mats?
Come on, I came all the way from Japan. No, I'm kidding.
Everyone, please put your hands together for Vicent.
Thank you.